So today begins a series of 6 lectures on the more detailed analysis of time reversal symmetry and its consequences and its violations. So this will contain some serious mathematics and physics. So it builds. So if you have questions, please ask. If there's something you don't understand, other things will build on it, and structure will fall. I tried to keep it as self-contained as possible. So we're going to talk today about the fundamentals of T-symmetry. I already yesterday, in the kind of general introduction, at a conceptual level, mentioned this striking phenomenon about the world, that time reversal T is a very poor symmetry of the experienced world, but a near perfect symmetry of physical law, with emphasis on near, as we discussed quite a bit. It's not exactly. And that raises 2 big questions. One, why is time reversal, given that it is a good symmetry of the physical laws, routinely badly violated in everyday experience, thermodynamics, radiation, in psychology, and so forth. And we mentioned the tentative answer, well, the right answer, cosmology, that there's only one, all you have to know about the universe is its origin in a Big Bang that was equilibrium for matter, but way out of equilibrium for gravity. Gravity is store equilibrium, making things clump, and that triggers all the other arrows of time. I also mentioned at the very end, the question of, could you actually imagine, in the style of Parmenides, that really time is not asymmetric and it doesn't flow at all, in fact, but it's like watching a river from the inside versus the outside, have a God's eye view, a perspective where nothing is changing, even though for those people living in the river and flowing along the dark. So that's speculative, but a very interesting kind of speculation. And then there's the question of, okay, given that all the arrows reduce to one arrow, why is there that arrow? And that's a profound question for next generation physicists to address. At present, there are no really good ideas about that. So, yeah. The asymmetry between matter and antimatter is widely believed to arise from a symmetric initial condition, also as a result of the dynamics of the Big Bang, which gives a direction to the reaction, and in combination to, where the flow of heat is unidirectional, things are cooling down, and that in combination with microscopic T violation can be reflected in development of symmetric initial conditions of an imbalance between matter and antimatter. So yes, that's another arrow of time. with a lot of interpretation. But the question we're mostly going to be focusing on is the second question. Why is there approximate time reversal symmetry in the first place? And I mentioned our best understanding of that is that it's an accidental consequence of deeper principles. If it were an exact symmetry, we could stop there and say, wonderful, we've discovered an exact principle of nature, but it's not exact. And so it's a wonderful thing that we can explain it in terms of things that we do more precise. And those are the basic principles of relativistic quantum field theory, or if you like, relativity plus quantum mechanics, and the deep symmetry principles of the standard model, which I will discuss in considerable detail in this program. And there too, this answer is not complete. We find that it gets us almost to an explanation of why T is as well obeyed as it is in nature. But there's a potential source of time reversal violation that does not occur in nature, or at least is very, very small, and there's no firmly established theory that allows us to explain that. But there are really good ideas that might lead to a theory that does establish it, and those ideas have experimental consequences. They lead to axions, a hypothetical particle that actively search for, that could very well supply the dark matter of the universe, but it hasn't been discovered yet. And we'll be telling that story from 2 or 3 lectures. Okay, so that's a preview of where the context of what we're going to be discussing and where we're going. So let's begin then at the beginning, the foundation of this whole line of reasoning. What is time reversal in classical physics and then in quantum mechanics before we get to quantum field theory, profound theory, that fundamental theory of nature? Let's start with sort of historical but also very useful review of the status of time reversal in more elementary theory. So the basic problem of Newtonian classical mechanics is you're given an equation, F equals ma, that tells you that particles obey forces that are just functions of position, at least in the simplest version of Newtonian mechanics. And then if you're given the positions and momenta, or velocities of all the particles to start off with, you can solve the equations uniquely. So you get a solution. So that's the initial value problem, the fundamental problem of classical mechanics. And it has the consequence that if you're given, instead of the initial conditions that you're given a different set of initial conditions, where you reverse all the velocities, you can use the same solution, reprocessed a little bit, to get a new solution with those initial conditions. Namely, straightforward mathematical manipulation to show that this solution, which evolves in time according to the opposite direction of the solution you started with the other positive, you can verify that this is a new solution with the flow of time in the opposite direction. So this is the fully spelled out, rigorous statement of time reversal symmetry in Newtonian mechanics. It allows you to construct new solutions from old solutions. To describe that situation, you say that Newtonian mechanics has time reversal symmetry, and notice we reverse the directions of velocity, both in the initial conditions and the solution. We say that, but we didn't change the positions. We say that the positions are even under time reversal, while the velocities are odd. Odd quantities of things that have to reverse their sign when you apply. So I spelled this kind of solution construction out in complete detail for Newtonian mechanics. I won't do that again. When we look at more complicated situations with more complex set of equations, the basic idea is always the same. You should think about initial values initial values of things that are even in time and not are odd in time. But I'm not going to go through all those steps over and over again. So now let's move on to electrodynamics. Now I'm going to just spice it up a little bit. I'm going to use the equations of the electrodynamics of axions. So these equations will occur in several contexts during the lecture. You can use them already to illustrate time reversal in a more complex situation. Okay, so these equations are invariant under a time reversal operation, but to identify that operation, we have to think a little bit. We want, in electrodynamics, we want the electric field to be even under time reversal. We don't want to change the direction of electric fields when we reverse the direction of time. Why? Because electrodynamics will be incorporated into ordinary mechanics as well, and the electric field will exert forces on charges that are the value of the charge times the electric field. We don't want the forces will be even under time reversal. We want the charge to be even under time reversal. So the electric field must also be even under time reversal. You could choose to make you could choose other conventions, but this is the way that the most straightforward way to construct a useful time reversal symmetry operation that accords with sensible definitions. So we start by making the electric field even under our transformation. Then, if we look at this equation, if we want this one to be time reversal symmetric, there's a d by dt here, so we need to make the magnetic field odd under time reversal. The left-hand side is and then we have two odd that will also be even, not change sign. So that's good. But now let's look at this one. Okay, we've made E even, E odd. Derivatives don't involve spatial derivatives, don't involve time. So if we want the right-hand side to have the same time reversal transformation as the right-hand side, we have to say that the A field is odd under time reversal. So we get minus sign and another plus sign. Yeah. A is the axion field. Well, that's a long story which will come. For now, it's just a field that appears in the It's the classical field for axions. So if you have many axions in a coherent state, they can be described as a classical field. That would be the A field. If you move to quantum field theory, everything has to be a quantum field. It becomes a quantum field. It's the same equation. It's a spin zero field. It has no other indices. So it's just, unlike these guys, it's a vector. I'm not writing arrows and so forth everywhere. But the A field, yeah, so that's a good question. A is just a scalar field, no other indices. Not scale, I shouldn't say scalar, it's spin zero. It turns out to be parity odd also. So it's pseudo scale. Spin zero. Okay, so now we have no more freedom, and we have to check that the other equations are also time reversal invariant, and I'll leave it to you as an exercise. Well, so this is odd. This is triply odd because it's A, time derivative, and B. That's odd. And then this one is also odd. What's that? I left them out. You can put them in. So if you do that, you'll see that very sensibly, charge is time reversal even, current is time reversal odd. Or conventional sources of electric and magnetic field. And by the way, I will, throughout these lectures, be using units in which the speed of light is the measure of velocity. So c equals 1 in our units, and Planck's constant is the unit of action, so h bar will always be 1. 1 will be left out of all the equations. We can go one level deeper in electrodynamics, and we have to, expressing it in terms of the potentials, which are the more basic dynamical variables, and express electric field in terms of potential. And we want E to be time reversal even. Here's the T. So the vector potential has to be time reversal odd. And the scalar potential has to be time reversal even. Right. And here, the vector potential is odd. With a sigh of relief, we know that's consistent with what we want. So, he has his doubt. Okay. So that means that the 4 vector formed from the vector potential A0, the scalar potential A0 and the vector potential A, transforms in a different way, the opposite way from T and X, from a normal 4 vector. And we say, therefore, that the A0A is unnatural. It's sort of a generalization of axial vectors, in this case for time, not space inversion. And it doesn't behave the way a normal vector does, but requires a minus sign. I'm sorry, the vector piece does, and the scalar piece does not. The opposite. Good. All right. So now we move on to quantum mechanics. And the basic equation is this. Schrodinger equation. This looks problematic at first glance for time reversal. The Hamiltonian is the energy, mv squared. That's even under time reversal. But here's a t. So the left-hand side looks like it's odd under time reversal. So we have problems, a challenge in making quantum mechanics time reversal symmetric. But there's a beautiful solution to that problem invented by Eugene Wigner, which is to say that time reversal symmetry is not implemented in the way that most symmetries are implemented in quantum theory, make a unitary transformation. Instead, time reversal is implemented with an anti-unitary representation. This is the definition of an anti-unitary representation. Instead of leaving the inner product of quantum mechanical vectors invariant, if complex conjugate changes the order. And also, if you multiply by a number, you don't get, it's not linear, but rather anti-linear. You get the complex conjugate. Why is that a symmetry operation of quantum mechanics? It changes amplitudes, but it leaves probabilities invariant. So it's something that leaves the physical content invariant, even though it changes the form. So in equations, we find that this gives, by u here, change the sign to t, we pull to, that's equal to this, as long as u h times u inverse is equal to h, so we have time reversal. Change in the sign due to having u act on I, cancel because we change t to minus. Symmetry time reversal. The Hamiltonian stays the same under this unitary. So, in the ordinary quantum mechanics of a particle under a potential, or multi-particles under potentials, for chemistry, if you like, the first approximation to chemistry, if you ignore spin, just have forces, Coulomb forces, then the Hamiltonian doesn't contain time at all explicitly, so you expect it to be time. And you don't have to do anything to make it time reversal invariant, except complex conjugate wave. And this also works, just complex conjugating the wave function, if you change the derivative into covariant derivative, which is the way you incorporate electromagnetic interaction. Because we've just convinced ourselves that a mu should be unnatural, x is natural, I changes sign, so it makes something that's natural, something that's unnatural. The whole thing transforms consistently, it's unnatural, and when you square it, you get the del square thing, in the Schrodinger find Gordon equation. Uh, square. So ordinary quantum mechanics, including electromagnetic interaction, is time. Now let's, as a very instructive example, which will be a gentle introduction to what we need to do in the standard model, let's consider a generalized multi-component Schrodinger equation with several different fields, the internal index K, and the most general kind of mixing and kinetic energy, and then also potential. So remember, the operation we want is that on the Hamiltonian, we multiply by a U and a U inverse, as well as complex conjugating. Some matrix U that's going to act on the U and U inverse. We want to see the same. That's the condition for U will also act on psi. So with complex conjugation, it also acts with U. And U is up to us. We try to find time reversal symmetry. Even if it's hidden, we want to construct a transformation that implements as much symmetry as possible to do. Okay, so we try to simplify this equation by using the right kind of variable. So we redefine the field in terms of which we want to express it. We're allowed to redefine things, bookkeeping. So if we make a unitary redefinition by multiplying our three-component field as an index K, three-component field by just reshuffling. So this is the computer science arrow. Means we replace this. Then we diagonalize. Then we can diagonalize. K was kinetic energy. We want that to be diagonal because unless you're a neutrino physicist who wants things to oscillate as they move along, it's convenient to use a basis. So we can diagonalize it by making a unitary transformation. It had to be, I should have said this, it had to be a Hermitian matrix in order that the Hamiltonian is Hermitian. So we can diagonalize it. And then positivity of the energy requires that the entries of K are positive. And in the Schrodinger equation, we would call those things 1 over 2m, 1 over the mass, 1 over twice the mass of the particle. The standard form for the Schrodinger equation. Even though we started with something that looks more general, after redefinition, it's just three coupled Schrodinger equations. The kinetic energy part is more or less normal. And now we'd like to implement our time reversal as complex conjugation, but that'll only work, it'll only be a symmetry if it leaves the equation invariant, and that requires that V is not just Hermitian, but also real. Otherwise, when you complex conjugate, it turns into something else. So V, for the Hamiltonian to be Hermitian, V has to be Hermitian, but it doesn't have to be real. So we're in danger of violating time reversal. or we're learning how complicated the system has to be in order to violate time. So now, if let's assume that all the masses are unequal. As a technical thing, you can, as a homework problem, think about what happens if you don't assume. Then the only remaining degree of freedom, if we want to keep the kinetic part diagonal, the only thing we can do now, we can't mix the fields anymore. All we can do is multiply them by phase factor. But we can redefine the field still by phase factor and try to make the V real. So, if we have two components to our V, then we can do that because there's just one off-diagonal piece in V, and so the relative phase can be used to make that real. And V is Hermitian, so once off-diagonal pieces are real, the whole thing is real. And we have universal. But if we have three components, can't do it anymore. We have two relative phases, but three complex numbers, you can't make them all go away. So for three or more components, there are opportunities for time reversal violations to appear. So it's a very interesting situation. We almost have time reversal symmetry as a consequence of other deeper principles, the Hermitian character of the Hamiltonian, and its basic structure in this case. But if you have only two components, then it really is automatic that you have time reversal, whether you build it in or not. Time reversal may involve transformations among different fields than you started with. You have to redefine things and be clever about it. But there is a valid time reversal operation, more simply expressed in terms of those redefined fields, but valid in general. And but with three or more components, we can start to have a bit of P violation. Now let's bring in spin. So far we've left out spin, and spin is subtle and beautiful. Context, well, in fact, in general. And we want to have spin, the spin of things, behave like an angular momentum. It really is an aspect of angular. And angular momentum, we certainly want to be odd on the time. It's R cross V, if you like. Odd. So we want, when we make the time reversal U operation, which may include complex conjugation, we want the spin to change sign. So, how do we do that? Well, we use the standard representation of the sigma matrix, the Pauli sigma matrix. I assume since no one is asking, then sigma 2 is imaginary, but the other sigmas are real. And so if you separate out the complex conjugation and then have a sigma 2 here, you have sigma 2 and then sigma 2 inverse minus sign, or sigma 1 and sigma 3. With sigma 2, you don't get a minus sign, but you get a minus sign because of the K, which complex conjugates. So with this definition of what U is, we can make the spin transform in the way that it should under time reversal, so that if you combine it with angular momentum, they're consistent with each other. Okay, now we're already prepared to make a profound deduction that you see has very from these considerations. This is Kramer's degeneracy. So because U, when you have spin, is sigma 2 times k, that means that U squared is minus 1. And therefore, if you have a system that involves n spin 1/2, when you act on that system with the generalized U, that gives sigma 2 for every single spin, and then an overall. This U squared is minus 1 to the n. So this was n equals 1k. And that means that the wave vector and its time reversal conjugate, U acting on the wave is 0, equal to minus itself. Here's the algebraic proof. U operation was anti-unitary, so it's applied on both sides. Flip the direction here, or alternatively, conjugate. U squared is minus 1, so this is minus. Now we see that this is minus product. So the inner product of wave function with its time reversal transform is 0. They're orthogonal. They have, but they have the same energy by hypothesis. If the system is time reversal invariant, energy is. That means every state in the system is degenerate. It has a twofold degeneracy. Degenerate, same energy as the orthogonal state, namely its time reversal. That's Kramer's theorem, and it gives a Kramer's degeneracy. Rigorous. I mean, I proved it sort of in a restricted framework, but this is a rigorous result that can be proved under much more general circumstances. A lot to do with the fact. Spin 1/2. If you rotate around by 360 degrees, you get a minus. Goes very deep. All right, so that's one profound implication that we'll be making use of. Another profound, but also simple application is to dipole moments. So if we consider what a dipole moment looks like inside a Hamiltonian, a magnetic dipole moment is, or the spin, the magnetic dipole moment interaction of an electron or particle that has that spin half. And that's fine. That's time reversal invariant because B is odd sigma. But if we try to do a similar thing for electric field, it's perfectly rotational invariant, but odd under time reversal. So the existence of an electric dipole moment for something like an electron or a muon would be a sign that time reversal is violated at a fundamental level. Now, those of you who studied chemistry in high school should be shocked by this, because if you look in a chemistry book, you will find long tables of electric dipole moments, which are not zero. Some of them are zero, but many of them are not zero. And chemists calculate these things. They're very proud of calculating. What's going on? Is time reversal grossly violated? Good question. Well, if you think about that, we'll come back to it in later lectures. Let me sort of add to the tension by saying our most precise tests of time reversal invariance are things like trying to find an electric dipole moment with the neutron or the electron or the proton. Very accurate. I've come up with zero so far. So why is that different from some random molecule that does have it? Okay, so that was a quick tour of time reversal in Newtonian mechanics and electrodynamics and axion in elementary quantum mechanics and maybe a little bit not so much. Now we're going to step up our game and talk about relativistic theories that are a more fundamental description of the world. And it turns out that the story of time reversal symmetry, a foundational story, hinges on some rather special features of the Standard Model that are very deep and should be understood in the context of the Dirac equation, or can only be understood in the context of the Dirac equation. So we'll need to introduce or review some properties of the Dirac equation in order to formulate the Standard Model properly and be able to fundamental key violations. So this is the Dirac equation. It introduces a sort of generalization of those sigma matrices and these gamma matrices. And in order for this to be time reversal invariant, we want the gamma mu's to be unnatural because there's an I. Spatial components of the derivatives are even under time reversal. And so we want the spatial components of gamma to be odd under time reversal to make up for the I. And similarly, D0 is odd under time reversal. You get another minus sign from I. You need another minus sign from gamma 0. So it's unnatural. R will have time reversal symmetry, which we really want to have in the description of the world. find the right descriptions is being mathematical. Okay, so this is one way of satisfying the basic definition of these gamma matrices. Goes into the Dirac equation. Dirac called it the square root of the metric tensor. Zero, zero, base components are all zero. And this combination is the so-called Bjorking-Drell choice of gamma matrices. You can use any old choice. It's a theorem that concrete in terms of one particular one. If we choose that basis, then by the same sort of reasoning that led us to use sigma 2 times complex conjugation in the Pauli equation, in the non-relative incorporation. Now you can convince yourself basically again because sigma 2 is that this is the time reversal operation that makes the Dirac equation time reversal invariant. Details of this instruction important calculation conceptually just happen. There is a change. It reduces in the non-relativistic limit to the sigma 2 operator. Okay, so that's the time reversal operation. The other thing that's crucial is what's called chirality. And this is a lightning introduction to chirality. With these gamma matrices that anti-commute with each other, if they're different, square root of 1, if they're the same, this gamma 5, the product of all of them, anti-commutes with all the gamma matrices. Imagine you have any of the gamma matrices here, you pull it through, it'll give you 3 minus signs from each of the different. So this thing, which I show emission squares to 1, anti-commutes with all the gamma matrices, all gamma 0, gamma 2, and gamma 3. And since its square is 1, we also have projection operators, that is, operators whose square is equal to 1, that project out the things that have the piece of the spinner on the fuse. This separates, this gives you, this projects onto the space of minus 1 eigenvalues for gamma 5 plus gamma 5 squared 1. These are projection operators. Their sum is 1, and they're called projection on left-handed and right-handed fermions. And the reason that they're called left-handed and right-handed is if you have a mass 0 spin 1/2 particle, its helicity is conserved. That is the component of spin along the direction of motion. That's the left-handed. I won't do that. See that? That's called for massive particles, of course, that doesn't work because you can move past them really fast, relativity, and change the direction. So there's no relativistic separation. For massive particles, it's less right-handed, but for massless particles, there is. And a great lesson that stems ultimately from the work of Li and Yang, the discovery of parity violation. We know that left-handed particles have very, very different weak interactions than right-handed particles. And in order to incorporate that fact, it's been found that in fundamental laws, we have to make a distinction between left and right-handed particles. To make that in a strict, rigorous way, we have to start with massless particles and then build in the mass by some system. Okay, so if n equals 0, we can, in the Dirac equation, separate out the left-handed do this projection. If we have a mass term, the mass turns left into right. So the mass term is not arguing about moving past things. It ought to be impossible. Mass allow that projection. Yes. Yeah. Why what? Well, because time. I, so because time reversal is this. Well, you just have to multiply out. And, yes. So I didn't do the algebra, but I've checked it. I didn't show you the algebra. Conclusion. Very embarrassing. Okay, so now we have all the pieces in place to take on the profound foundation of approximate time universal symmetry in the world. And we have 10 minutes to do that, but that's absurd. So I am going to do only part of the derivation today. We'll stop at a sensible place. Okay, so first, let's take a census of what's in the standard model. So we have, first of all, the symmetries of the standard model. We have SU3, color symmetry, the basis of strong interaction. SU2, U1, which is mixed up a bit for the weak and electromagnetic interaction. And associated with these local symmetries are gauge bosons from the Yang-Mills equations, Maxwell equations, generalization. And the quantum fields that implement those symmetries are gluons in the case of SU3, W and Z bosons for the weak and electromagnetic. So that's one ingredient, and that's relatively simple. Doom. And then, so that takes care of the force mediators, if you like. That's all there is. Then the other ingredients are, the other ingredients, I should say, are, first of all, the fermions, all this stuff. So these are the quarks and the leptons, and then there's the Higgs particle. So let's first talk about the quarks and the leptons. The quarks here are written in red to indicate that they have color, so they have a color degree of freedom. But for our purposes, we won't need to spell that out very much. So that's going to be left explicit. The weak interactions, however, have to be spelled out. And so, and particularly, we have to have a distinction between left and right. On one hand, a doublet of fields that indicates that the SU2 transforms this doublet. So the SU2 is acting on this two-dimensional vector. It acts only on the left-handed fields. That's the great discovery of Li and Yang. The weak interactions only cares about left-hand, well, with more development, basically that the left-hand, the weak interaction only involves the left-handed fields, so we have to make that distinction between left and right. And similarly for the leptons. Now, these U's and D's, as we'll elaborate, are the up-tight quarks and the down-tight quarks. So they actually have three flavor components. So capital U implicitly has not only color indices, but also flavor indices. We'll be having to massage that quite a bit. So that to be understood. So this U field includes the left-handed components of the top quark, the charm quark, and the up quark. And the D field here includes left-handed components of the bottom quark. The other thing that should be explained here are these funny numbers. These are the so-called hypercharges. They are the charges under this U1 group. Okay, so they're not quite the electric charge because the photon is not quite this U1. It's a mixture of the diagonal components of SU2 and U1. The way the Higgs field back to the value and mixes SU2 cross U1. But it's almost the charge. In fact, what it is the average charge of the average electric charge of the fields that are in here. So the charge, the up-type quarks have charge 2/3. The down-type quarks have charge minus 1/3. The average is 1/6. And that's what appears here. And we have just the right-handed up quark, it's 2/3. The average is the same as the thing. We have this one. And then, so these are spin 1/2 fields, and that's all of them in the standard model. And then finally, we have doublet under the weak interaction. The average. Okay, so that's the census of the standard model. Now, those are the things, the building blocks out of which it's built. We also need the operating system, how these things play with each other. And the operating system is also remarkably simple once you understand relative and gauge symmetry. There are only a few kinds of interactions that appear. One is the derivative that allows the field at one place to communicate with nearby places and allows things to move. So these are the kinetic terms. And we have the covariant derivative, which is the ordinary derivative, plus the gauge field. I won't review how local symmetry is constructed. We'll just have to fill that in. But basically, this is a generalization of electrodynamics scalar and vector potential. In the case of non-abelian symmetry, and SJTU, these become matrices instead of numbers. And from this covariant derivative, the derivatives in different directions don't commute with each other. If you take the commutator of them, that's something, since the covariant derivative transforms nicely in the gate, so will the commutator. And this is the way of getting the fact that curvature, derivatives in different directions don't commute with each other. That's a sign of curvature in this context, generalizing the notion of space. And the measure of curvature is what we call the field strength. A very beautiful understanding of what gauge fields are all about. They are kinds of curvatures in internal spaces. As things move around, they move not only in physical space, but in color spaces, internal spaces, if you like, and this is telling you what the curvature is in those internal spaces. Okay. Now, we want also to allow the gauge fields to move, so we need terms that involve derivatives of the gauge field, and to have something that transforms nicely, we constructed this F, and now we can make a term that's gauge invariant and relativistic invariant like this trace of field strength. So that's the internal time itself, something that's relativistic. This is a generalization of E squared minus B squared, which is ordinary electrodynamics. This is the non-important generalization. It introduces one parameter for each of the interactions. This is not what you would usually find in textbooks. You usually find G not here, but in the covariant derivative. That's just a redefinition. Okay. You find G propagating in different places. This is a much clearer way and a more profound way to do it, because for one thing, it shows you that there's only one G. How many covariants? There's another way we can put together these field strengths in a way that's relativistically invariant and gauge invariant, and that's this. And this will be the fulcrum around which our subsequent discussions will largely balance. This is the so-called theta term. It's another way of putting together field strengths in a relativistically and gauge invariant way. Interactions or basic principles are concerned. It's a generalization of what in electrodynamics would be the E dot D. Like non dot. And this is T odd. Why? Because you have four vectors appearing in this, and two of them, namely the ones that come from derivatives, are natural, and two of them are unnatural. So altogether, it's natural. One of them is a time derivative, so there's one minus one. One of them is a t, so one of them is 0, so there's a minus. all the unnatural about natural expectation. Okay, so that's one building block. That's the kinetic energy for the gluons. Then we have the kinetic energy for the fermions, which we can build using those covariant derivatives. Yeah. Projected, and then a couple of footnotes. One is that the relativity, you have to have used psi bar instead of psi constant, bar zero, and that means that chiral projection factors 1 minus 2. Then you have to pull it to a gamma zero, to a gamma mu, so you get 2 minus from the fact that it can't vector. So that kind of kinetic energy only works separately in the left hand and the right hand section. And then finally, the other kinetic energy is the kinetic energy of the Higgs field. And that's it. That's it as far as propagation is concerned. This is at the same level, I believe, and it in fact goes together very naturally with the formulation of general relativity, where you have covariant derivatives to see how things move along, and you have curvature from commutators of the covariant derivative. This was described in words by Wheeler. Of course, the physics is due to Einstein. Says that, but Wheeler summed it up in this nice poetic way, that matter tells space-time how to curve, and space-time tells matter how to move. Matter couples, non-cubing equilibrium, relativity would be the Kuznetsov symbol, things like that. So it feeds back and makes the, when you solve for the gravitational field or the gauge field, you find those matter affects it. And on the other hand, matter motion is described by the same covariant derivative, so it moves as straight as it can in the presence of the curve. So here, it's really exactly the same, with just a change of a few words. Charges tell gauge field how to curve, and gauge field tell the charge how to move. Or charges tell internal spaces how to, so internal spaces how to curve. Okay, so that's the kinetic energy part and the curvature part. There's one more ingredient. Those are like the kinetic energy terms. There are also potential energy-like terms. Those involve the Higgs field. And there are 3 comments to make about this skeletal. First of all, here, instead of having 2 gamma matrices, you just have the one, you just have the gamma zero. And so the projection operators don't work, all right? When you pull it through, you get one minus sign, so it projects, say if it's projected on the left here, it projects on the right over there. So this is where the left and right sections meet one another. If we go back, let me make the statement, then I'll go back and show you. If you look at the census of the standard model, and you want to connect left-handed fields to right-handed fields in a way that's gauge invariant, then the term has to be overall neutral. That's what gauge invariance means. But the left and right-hand components never match. So you need something, a fudge factor, if you like, to make it work. They never match because the weak interactions only work on the left-handed guy. So you can't make a singlet out of something that's a right-handed piece that's a singlet and a left-handed piece that's not. You need something to absorb the transformation, and you make the Higgs field a doublet to do that. You need terms like this because the fermions we observe in the world, the quarks and leptons, aren't mass zero. How do you get mass from this? Well, you get mass when in empty space, the Higgs field has a non-zero vacuum excitation value, or a V. You just put a V here, V can come essentially like mass. Finally, the very last piece of the operating system is the Higgs potential, the Higgs self-interaction. And there's a mass-like square. And this is used in order to encourage the Higgs field to take a non-zero vacuum excitation value at minimum energy, include a negative notice. The potential terms are not as beautiful as the kinetic terms. There are no poems by Wheeler that tell you that praise the potential terms. They are like, in relativity, they're like the cosmological terms. And it's ugly thing that you need. This is a very good place to stop. So let me stop here, and we'll continue next time in this place. Let me just show you. Let me sort of preview where the argument goes. So I've showed you ways of building in the general principles of gauge invariance and getting things to move and getting things to have mass and getting gauge interactions that we use in the standard model. The crucial point for this the analysis of time reversal symmetry as a consequence of these principles is restraint. You can't keep adding complications because we saw even in that simple quantum mechanical model, that is, you add complications, time reversal ceases to be valid. But fortunately or unfortunately, the singularity, the difficulty of constructing a system quantum field theory means you have to use great restraint in what terms you can incorporate. You can't incorporate terms that have complicated products of many fields or lots of derivatives. Those don't lead to quantum fluctuations. And but I'll just show some pictures in this lecture. So this is the yoga of restraint. Occam's razor. That is something that's strictly justified in the context of quantum field theory and standard model. All things being equal, the simplest solution. That's one. These are heroes, principles, gauge symmetry. The philosophy that I'm showing you applied to the standard model was applied more generally to analysis of condensed matter systems. Heroes of that particular development are Landau and Ginsburg. This is a very selective choice of heroes, but it's nice to have at least some pictures here. And then finally, Steve Weinberg, who in the recently deceased, in the context of the standard model altogether. Nice package. So now, yeah, I can't do it except by clicking. I just wanted to get a couple of punches. Clearly, you have to have the lecture to do. So you'll get T symmetry up to a very good approximation, rigorously defined from the nature of the standard model. We'll see why Kobayashi and Maskawa got it. And then we'll see the villain, or the thing that shows why the thing they missed, which is going to be the story of leading into axions. That's the theta term, which shows that you don't have a full is valid, but almost. And then I'll stop with this. This is the roadmap of where we're going to go in the next couple of lectures. We'll show that that theta term has physical significance, and it actually, the fact that it's physically significant, solves an important problem in QCD, the so-called U1 problem. So showing that it's physically significant is not trivial. Why don't you see in electrodynamics books, in textbooks, E dot B discussed? Well, why don't you? Because it doesn't contribute to the classical equations of motion, total derivative, and so it doesn't contribute to the equations of motion, and so in classical electrodynamics, it's negligible. To show that it's not negligible is a profound exercise in quantum field theory, and it's crucial for QCD to describe the world correctly. But it introduces another problem. It means that that theta term, which we saw violates time reversal symmetry, is physically significant. You can't say that it doesn't. This has got to be in order for QCD to work properly. So that solves one problem but introduces another, and that's the story that will lead us to axion and dark matter and all those good things. Okay, so I think I'd better stop there, and we'll continue this discussion next time. But now let's have some questions. Yeah. The Maxwell axion electrodynamics. Is there some way I can navigate this without having to click dozens of times? I'd like to go back to an earlier slide to answer the question. Yeah. 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 You can ask the question while we're finding it. Oh. Yeah. Yeah. Oh. Oh. No. Yes. That one. So these are the equations of axion electrodynamics.
We know that axion is to solve the strong CP problem.
Yes.
So it introduced the CP term. But why once we introduce their equation, there's no CP value, or there's no time symmetry?
These equations?
Yeah, do you mean that once we should we introduce the fermion so that there is the same symmetry, reversal of symmetry?
Yes, you have to include terms that are neglected here in order to see the overall series. It still has the Kobayashi-Masawa interaction, and it also well, and it could also, we'll talk about it, but basically this is neglecting the Kobayashi-Masawa kind of time reversal violation. And if you do that, this is a very good, this is for as far as pure axion physics. So this is an accurate representation of how it interacts with the electric field. So there are other interactions elsewhere in the description of the world that violate time reversal, but this does not.
Yeah, just like E dot D doesn't influence.
Yeah, well, E dot D, let me give away the story. So E dot D is time reversal odd.
Yeah.
So if you have theta times E dot D, that's time reversal odd. That's bad. But if you have A times E dot D, if you change that theta into a dynamical field, you can make, it's not a number anymore, it's a field. And if that field interacts in a way that's P and P odd, particular time, if it's time reversal odd, then A times E dot D is time reversal even. And you get time reversal invariant equation out of it. That's where these come from. This together with that term together with the ordinary maximum. So this is coming exactly from Lagrangian A E dot B with some coupling.
Hi, Frank. I have a question that in some basic theories, we always treat time as a scalar. So is that possible for time to have more than one dimension? So,
well, it's a very interesting question whether time could have more than one dimension. It's quite a few paradoxes arise if you try to make time more than one dimension, which I hadn't planned to talk about. So, it's very problematic. So it's a logical possibility, but seems to be very difficult to make it physics. Physics thrives on initial value problems, and we've built up a rich description of the world based on that. If I had to guess, I would guess that it's more likely that we get rid of time more than instead of doubling it. Okay. So derive time as a version of space. And that's what relativity is.
Hi, professors.
Yes.
Thank you for your wonderful lecture. And I have a question which I have it in my mind for a long time.
Great.
Since I've learned quantum mechanics. That is, we think angular orbital angular momentum has time inversal odds properties, and we think that the spin orbital momentum should have a similar behavior with the orbital one. So we think that it is also odds in the time reversal. Yes. I would like to know whether do we have another more fundamental elaboration or more fundamental reason?
That's a very, very deep question. And the answer is that finding symmetry is a creative operation. So saying a set of equations doesn't have symmetry doesn't tell you very much about it. Saying that they do have a symmetry constrains their property and tells you you have very special equations and has, of course, physical consequences. So we don't, in a way, how should I say, we create time reversal transformations that leave the equations invariant. And if we want to have a useful definition of time reversal, we really don't want to break up angular momentum, spin, and orbital faults. That's not the way it actually happens in relativity. Transform into one another. So if you want to have a theory that's relativistically invariant and has a reasonably simple balance, you really force to have an orbital transform the same way. But the basic answer is that defining the symmetry is a creative operation. So you guess, and the right guess, the obvious guess.
How come? You just made two analogies. One is quantum theory and the general. One is math tells us the space-time for the curve. Mapping. And the other one is you say that the self-interaction term in this Higgs field has some relation with cosmology constant.
Yeah.
Yeah. Can you give some little more detailed explanation how this mechanism works?
Well, that analogy is much looser. It's like a potential energy in the sense that it doesn't contain any derivatives. So it's strictly local. The field interacts with itself at the same point. And the other thing is that it's ugly. Whereas the others are kind of beautiful and very tightly constrained. Potential terms is much less constrained. Einstein himself said, with respect to general relativity, this was of course before the Standard Model, he said, you have an equation that says curvature equals energy momentum tensor. Strictly, it's the Ricci tensor equals a constant energy momentum tensor. And he said the left-hand side, the curvature, is like a palace of gold, and the right-hand side is like a shack of wood. And okay, now we know enough about the energy momentum. Some of the left-hand side, the gauge field pieces, I think, and the kinetic energies are golden. They really have a geometric interpretation. They're very constrained. I mean, for each gauge group, we had one coupling, just like the gravity. There's one basic coupling, and everything else follows from symmetry. You have covariant derivatives. It's very unique. Whereas when you start to discuss the Higgs sector, as we'll see, and it's notorious, many different couplings occur. So that's reflected also in the existence of many different masses for quarks and leptons and weak mixing angles. So it gets very complicated. The Standard Model is much more beautiful without. So that's, or also in quantum mechanics. This goes way back in quantum or even classical mechanics. The kinetic energy, the MA, is very unique and constrained and nice, but the forces could be anything. Well, Newton told us about gravity, but otherwise people put in springs and things. What about force fields? And it was kind of unconstrained. So that distinction between kinetic and potential has a long history, and it's still with us. Gravity is the cosmological term, and in the Standard Model, it's the Higgs sector. So all the stuff that doesn't involve derivatives, that doesn't involve motion.
Thanks. I have two questions. The first question is, before the Big Bang and after the Big Bang, the time translation invariance is obviously violated. Therefore, the energy is not conserved.
Yeah.
Therefore, there is all of a sudden there is a large amount of energy in the universe.
With the Big Bang?
Yes. And then how do you describe the event with the physics? Is the general relativity?
Okay, well, there are several questions in there. So let me start with the most basic. The time translation symmetry is a property of the equation, not of the solution. So even going back to the early universe, the equation, the basic equation, is the same equation, still allowing it to change the origin. The solution is quite different. The solution is not special event, Big Bang, and there's a history that unfolds in one direction of time. And you asked about conservation of energy. Conservation of energy is straightforward in a bounded system. When you apply it to the whole universe, especially in general, it's not straightforward at all. So you can't sort of integrate up the energy locally. In fact, in general relativity, basically there's a cancellation. This is oversimplifying a bit, or quite a bit, but the spirit of it is not wrong. So you have ordinary kinds of energy, but then you also have gravitational energy. And in general relativity, because curvature is related to the energy density, it turns out that if you integrate over the whole universe, it all cancels. The energy of the whole universe is just zero. And that's because you have a trade-off between gravitational energy, gravitational potential energy, other forms. In a big universe, the gravitational energy is a lot, and so it can cancel off. Coming from distant regions, a lot. What appears to be a lot of I don't know if that answers the question. Make it obscure. So the application of conservation of energy to the universe as a whole is very tricky.
My second question is,
But what you said is also correct. If you forget about gravitational and just look at the matter system, take the expanding universe as a background. You just don't ask where it's coming from as a solution of equations of gravity. Take it as a background. Of course, it's a time-dependent background, and energy is not conserved. So in that model, energy is just plain not conserved because the universe, you have time.
and the second question is, in a four-dimensional universe, D is a tensor, and it has 6 components, and E is still a vector, it has 3 components. Therefore, you cannot do E for D. And then how do you, there's something problematic.
No, both B and E have 3 independent components, so it's relative to
I mean, in a four-dimensional universe.
in a 4-dimension. So in this F nu field, the electric field is the ones that are F sub 0, 0I, or I0, and F is antisymmetric, so there are 3 components.
Yes, I know.
And the magnetic field are the Fij's, and there are 3 independent components. There's 1, 2, 1.
Yes. But I mean, in a four-dimensional universe.
In a 4-dimensional universe, I'm talking about a 4-dimensional.
No, that's three-dimensional space and one-dimensional time.
Yeah.
I mean, four-dimensional space and one-dimensional time.
Oh, no, then you wouldn't have this. Then it's different. Yeah, then it is different. It's a theta, you wouldn't have the theta.
Well, wait.
Yeah. But our universe is not. At least.
Thank you, Professor, for your lecture. And problem about the quantum mechanics part of your lecture. You mentioned that there are 2 components.
Yeah. Yeah. Oh, well, this was just a model. It was not meant to describe any specific physical system. But as you'll see, that model contains the essence of how time reversal violation arises in the standard model, but in a simplified form. What are the examples? They're examples of different things. so, so they might be things like an electron. We're talking about wave mechanics of particles, so it might be an electron, a hole, and a phonon, something like that. It could be anything. Could be electrons in different bands. So anything that has an index that allows the distinction. Okay. All right. This is, oh.
So
Isn't it? Isn't it? Oh, very similar to this. Oh, I